Hey guys, this is the last countdown video. Pretty exciting, so let's get to it. This was the second free response question in an example, and you should, if you want a blank one of these, just email me and I'll email you a blank version. And then you can go back to watch the video and see if you got it right. So this one's really focused on probabilities and categorical data because the other one was quantitative. So let's take a look. It says 9 sales representatives, 6 men and 6 women, were at a small company and they wanted to attend a national convention. They only had enough travel funds to send 3 people. So the manager did select the 3 people and 3 people were chosen, but those were women. So this concerned the men greatly and they were wondering, that's highly unlikely. Exactly what would have been the probability of the 3 people you selected from the group, 6 men and 3 women, that would result in getting all the 3 selected to be women? So the first thing I did is just calculate in my head, what's the probability of getting a man? And there's 6 men out of 9, right? And then I thought, and then what would be the probability of getting a woman? If you were only selecting one, there's 3 women out of a total of 9. Okay, so that's kind of the first thing I wrote on the problem. Then we have to think to ourselves, we've got to pick 3 picks. So if you're thinking about this, the first time you pick, and you pick, the probability of picking a woman is 3 in a 9. But now the second time, the probability of getting a woman is less because you've already picked that other person. So see, now you only have 2 women left to pick from, and you only have 8 people in total. And then you've also got to pick a third person to go. So the third time you pick a woman, the probability of selecting a woman, there's only 1 woman left out of 7. And then you need all these events to happen at exactly the same time, which is why I had to multiply 3 times 2 times 1 in the numerator and 9 times 8 times 7 in the denominator, which gives me a very low probability. So this brings me back to the very first day when we calculated the probability of that lady smelling Parkinson's was so rare. And where is that threshold for rarity? So I think you've learned that nationwide, unless we send a different standard, our reason to doubt is at 0.05 unless they tell us otherwise. So part B says, would there be a reason to doubt the manager's claim that this really was selected at random? And you should say absolutely yes. So yes, since this number, the probability we calculated, is less than 0.05. This sounds like a conclusion on a significance test. Since that number is less than 0.05, it is unlikely to occur based solely on chance. And that's that's the definition of what a p-value is. And so you've actually done it by hand. Okay, so because it is highly unlikely, we actually do have sufficient evidence to doubt the manager's claim that the 3 people were selected at random. So notice I'm just recopying what it is they asked me to figure out whether it was reasonable. Okay, so part A and B done. Let's look at part C. It states, I'm going to have to erase a little bit and then I'll rewrite that, but let's read this scenario here. It says, an alternative to calculating the exact probability is to conduct a simulation. So this is very popular to show up on an AP test because we did so many simulations all year. All right, so if we did a simulation, would this simulate the information we did up above? So this scenario, would this simulate that? And vice versa. So it says, and I'm just going to kind of start making little sketches to help me think about this. It says, in each trial, the simulation consists of 3 fair dice. So I kind of jot down a little a little picture just to help me kind of picture what would happen. And then 1 die for each convention attendee. So this would be who goes the first, who goes the second, who goes the third. Then it says for each die, rolling a 1, 2, 3, or 4 would represent a man, and rolling a 5, 6, or 7 would represent a woman. Now, just kind of checking what I checked up top here. I rechecked this, and if I force the ratio 6/9 to be out of, so that would reduce to 2/3, and if I force the denominator to be a 6, notice that is the correct probability. So 4 outcomes out of 6 would match the probability we found above, and 2 out of 6 would match the probability we found above. So that part's good. But now they're saying after 1,000 trials, would this indicate the number of the 3 women selected? The part that you should be questioning in your brain is, notice up top, if that was true, then our calculations up here would have been 3 out of 9 times 3 out of 9 times 3 out of 9. Or on the dice, the probability of getting a woman was 2 out of 6, and getting a woman here, 2 out of 6, and getting a woman here, 2 out of 6, right? But the problem is that's not the probability of getting all 3 women. This probability is not equal to the one we've shown above. So the reason what's happening is, notice the denominator is going down. And so that's what they're looking for there. And you could show that with the math I explained here. You could show it with this and kind of a picture. But we also want to actually answer the question in words. So it says, does the process proposed correctly simulate? Does the process proposed correctly simulate? So I'm going to repeat those words. No, this simulation process would not correctly simulate the random selection of 3 women, from a group of 9 people, consisting of 6 men and 3 women. So I've copied my wording there. And then I have to do this explaining. So I try to explain, because the process listed above is done without replacement, and the dice is done with replacement, this is resulting in different probability calculations. Therefore, it can't be, a simulation would have to simulate exactly the same probabilities for it to be an accurate simulation. Okay. So this problem actually continues, maybe not this long, but this would be a good practice question. So it says, name the appropriate graphical display used to find an association between this data. So see how this is categorical data. So right out of our notes, a segmented bar graph would be the right representation. Some other correct answers would be a side-by-side, which we've seen in the practice problems, or the mosaic. Those would also be acceptable answers. So I actually took the time, you wouldn't have to do this for your test, but I took the time to show you what it would do, and notice this would be the right way to display this. Okay, now let's get to questions from this data. The first question is, what is the probability that a person is from the Southwest region? So notice, a person from the Southwest region, there's a total of 250 out of the full 5,000, so this is just a direct calculation. Now let's get to one that's a little more difficult. What is the probability that the sales representative is female or Southwest? So notice I've circled, here's all the raw data for female and the raw data for Southwest. And so you can add up these 4 numbers and put them over 1,000. And that's what I did here. This is typically how I do an OR calculation. Some students like to use a formula. So they would say, well, the probability of female is 400 out of 1,000, and the probability of Southwest is 250 out of 1,000. And then we have to subtract this overlap, right? Because they're not mutually exclusive. So either this way or that way, I still get exactly the same answer, 0.55. All right, next question's asking, well, what is the probability that the sales representative is female given they're from the Southwest? So notice this sets up a ratio. In the numerator, I had a total of 100 from the Southwest out of a total of 250 from the Southwest. So these numbers are coming from the table up here. There's 100 women out of the total 250 in the Southwest region. Okay, now here is a classic question. I would not be shocked. They love asking this question. What would be the, when selecting this representatives, are the events female and serves in the Southwest independent? Well, there's a couple ways to assure this, but I usually just go in the order they ask. So they would be independent if this is a true statement, and this is written on my cheat sheet, so that's why I used it. So we know that if this is true, then they're independent. So if the probability of female is equal to the probability of female given Southwest, then we will know they're independent. So notice the probability of female is just 400 out of 1,000, right? And the probability of female given Southwest, we just calculated. So it's still 100 out of 250. And both of these are the same ratio. So my answer is yes. But notice I actually give words. I actually answer my answer in words. Yes, the events, and I copy it from the table here. Yes, the events is female and serves the Southwest are independent events. Okay, last question. It says the convention organizer with a list of attendees plans to randomly select names until they get a female who serves the Southwest. Is this binomial, geometric, or neither? Now, right off the bat, I'm thinking, I see this word until, and I immediately know it can't be binomial, because a binomial, you have to know the fixed number of trials. Okay, so that one has been eliminated. Then we have to decide if it's geometric. So geometric requires us to go to the 4 standards bits, right? The issue here is because there's a problem with the fact that the probability is not the same each time. Notice the first time we go to pick from this group, the probability is 100 out of 1,000 women, right? 100 women. Wait a minute. 400 out of 1,000, right? Oh, wait, it serves the Southwest. That's why I put 1,000, sorry. There's 100 women in the Southwest, right, out of the 1,000. And then if the second time I haven't picked her yet, there's still 100 women from the Southwest to be picked, but now I have fewer people to be picked from. So notice how this probability is not the same each time we pick. Therefore, I must say neither. All right, guys. Hope to see you in one of the live lessons. Good luck.